Welcome to a new addition to the Walz tutorials. In an earlier tutorial, different aspects of fluorescence measurements were discussed. In the present tutorial, different aspects of WinControl-3 software will be discussed. If we would divide Walz instruments between more ecological, agronomical, and more physiological, then the instruments that are used for the more ecological, agronomical applications use WinControl-3 software, whereas the instruments for the more physiological applications use PAM-WIN software. More ecological also means, in the case of outside application, that fluorescence measurements are paralleled by ambient light, temperature and humidity measurements. Recently, the measurement of the spectrum of ambient light was added to this range. The instruments controlled by WinControl-3 are the MINI-PAM-II, which in this tutorial will be the reference instrument, the DIVING-PAM-II, WATER-PAM-II, MONITORING-PAM, MICRO-PAM, MICROSCOPY-PAM and JUNIOR-PAM. Categorizing these instruments, the MINI-PAM-II and the JUNIOR-PAM are general-purpose instruments. The MINI-PAM was developed for field measurements, but in the meantime its use can be extended by a range of accessories. The monitoring and MICRO-PAM were developed for the monitoring of multiple samples during longer periods of time. Fluorescence measurements are here standard paralleled by ambient light intensity, temperature and humidity measurement. The DIVING-PAM-II was developed for underwater measurement. The WATER-PAM-II, the most sensitive instrument of the range, for the analysis of water samples, either sweet or salt water. And the MICROSCOPY-PAM is used in combination with a microscope to allow the study of single cells. Apart from a discussion of the features of the software, the tutorial will also touch on some more physiological aspects of the four main applications of the software: monitoring, field measurements, induction with or without recovery, and light curves. Looking at the 7 different instruments, I want to note that what binds these 7 instruments is that they all use the saturation pulse method. What separates them is their application philosophy, the application for which they were developed. Again, I want to emphasize that I will use the MINI-PAM-II as reference instrument for my presentation. If you open the software and look at the top of the page, you will see 11 tabs. For the present presentation, 8 tabs are relevant: chart, induction curve, light curve, set chart, report, memory, batch and settings. Whereas the 3 other tabs, spectrum, control and sensors, are related to accessories I will not discuss here. These accessories are an oxygen sensor, a spectrometer, a pump and an external LED light source. The software opens in the chart window. This is the window where you, the user, have the freedom to do what you like. By clicking on the Start Online button, the instrument starts to measure, recording FT. What does this look like? Here you see the whole graph window. If I click Start Online at the bottom, the instrument starts to record FT, as shown on the right-hand side. For a dark acclimated sample, FT equates F0, the state with all the reaction centers open. When clicking the Start Online button, at the same time the Record Online box is checked. I can also do it the other way around. By checking the Record Online box, the Start Online button will be activated as well. In all windows, it is possible to start the FT measurement in the chart window by checking the Record Online box. This can be practical in the case of measurements of a light curve. The light curve window only gives the parameters, whereas the chart window then records the fluorescence intensities as a function of time. The recording can be stopped by clicking the Now Stop Online button or by unchecking the Record Online box. Before continuing with the other windows, I want to say a few things about two topics related to F0 and FM. The F0 dash value, that is the F0 value in the light, can be determined either mathematically or experimentally, and this choice is determined by the F0 dash mode box below the graphics window. If the F0 dash box is unchecked, the F0 dash value will be determined according to the formula of Oxborough and Baker. If the box is checked, every saturation pulse is followed by a far-red pulse to oxidize the electron transport chain and thereby allow an experimental determination of F0 dash. The length of this far-red pulse can be defined by the user. In the settings window, the width of the far-red light is defined. The default value is 5 seconds, and this is also the length of the far-red pulse following a saturation pulse. If the user accidentally would increase this value to 50 seconds, every saturation pulse would be followed by a far-red pulse of 50 seconds. Personally, I think that 5 seconds is rather long, and I would go for maybe 3 seconds and a somewhat higher far-red intensity, or even 1 second. It is possible, so you can test it. I want to show you now what the visual effect of these far-red pulses is. On the left-hand side, you get a traditional view of an induction curve, an increase followed by a decrease. When F0 dash mode is turned on, the fluorescence increase induced by the saturation pulses is each time followed by a deep valley. Please note that the F0 dash mode only works with internal light sources and not for field measurements made during the day. Ambient light strongly interferes with the effectiveness of the far-red pulse. An aspect of saturation pulses I want to mention here are the two saturation pulse buttons, the F0 FM and set button. Both buttons trigger a saturation pulse, but the software treats them differently. By clicking the F0 FM button, the user wants to determine the reference F0 and FM values that will be used for the calculation of parameters like NPQ, QN and QP. The measured values are put in the top part of the list of values, F0, FM and F0 FM, as indicated by the arrow. Clicking the Set button also triggers the saturation pulse, but the obtained values are treated as F or F0 dash and FM dash, and instead of F0 FM you now get Y2, the effective quantum yield of photon 2. In the list of values, these are placed more towards the bottom as indicated by the other arrow. Now the induction curve window. However, to define an induction curve, we first have to go to the settings window. An induction curve is defined by 3 parameters. The delay is the time between the F0 FM determination and the start of the actual induction curve. The default value is 40 seconds, but somewhat longer does not hurt. The second parameter is called the width. That is the time between the saturation pulses. The default value is 20 seconds. Less is not a good idea, and again, more does not hurt. The third parameter is called length, which refers to the length of the measurement, and which is defined by the number of saturation pulses applied during the actual induction process. The default value is 12, which means 11 times 20 for the 12 pulses of the induction process and 40 seconds of the F0 and FM determination. This adds up to 260 seconds, plus a few seconds at the beginning and the end of the measurement. Induction curves can be started in 2 different ways. By clicking the Start IC button, or at the bottom of the software, by clicking on the Program tab and then checking the induction curve box. If you check the IC recovery box, the recording of an induction curve will be followed by the measurement of a recovery phase in darkness. The light curve window works similarly. Again, first go to the settings window to define there the light curve protocol. The first parameter is the width. That is the length of each light step. The default value is 20 seconds. I personally use as a standard value for my light curves 120 seconds, that is 2 minutes per light step. The second parameter is the actinic light intensity setting with which the measurement starts. The default value is intensity setting 3. The third parameter, length, gives the number of light steps measured. Choosing 3 as starting level and 8 light steps means that the levels 3 to 10 are measured. Starting at intensity 1 and selecting 12 steps, all the light intensities available will be measured. Starting a light curve works in the same way as an induction curve. Click the Start LC button or under the Program tab either check the Light Curve box or the Light Curve plus Recovery box. In the case of light curves, it may be an idea to check the Record on Line box and record FT in the chart window. Otherwise, only the parameter values are recorded. At this point, I want to raise one other issue. Ask yourself the question, what is a normal light range for my sample, and adapt the light curve to that range. To apply 3000 micromoles of photons per square meter per second to an algae suspension grown at 50 micromole photons per square meter per second is not meaningful. So far, I did not touch on the with F0FM pulse box. If the with F0FM pulse box is checked, light curves and induction curves start with an F0 and FM determination. If the box is unchecked, the software skips this determination. Unchecking with F0FM pulse may be meaningful in the case of light curves. To avoid artifacts related to photosynthetic induction, it is a good idea to activate the Kelvin-Benson cycle by a pre-illumination. The sequence could then be 1. Click the F0FM button to determine F0 and FM. 2. Apply 2 minutes of pre-illumination, for example 50 micromoles of photons per square meter per second, or for extreme shade samples probably a somewhat lower value should be chosen. 3. Then start a light curve with the F0FM pulse box unchecked. There are two aspects of light curves I would like to illustrate. At a certain light intensity, the electron transport chain and the Kelvin-Benson cycle are in balance. If I now increase the light intensity, the Kelvin-Benson cycle each time needs some time to adapt to the new situation. If the light steps are shorter than the acclimation time, the electron transport chain will during this acclimation time be more reduced and the electron transport rate or ETR lower. On the slide, 2 experiments with begonia leaves are shown. The top panel shows an experiment without pre-illumination and the bottom panel with pre-illumination. The variable in both windows is the length of the light step, which was varied from 10 to 90 seconds of illumination. In both cases, you see that the maximum ETR value approximately doubles or even triples on increasing the step length from 10 to 90 seconds. Further, these panels show that in the absence of pre-illumination, mainly the lower light intensities of the shorter step lengths are affected. I will now return to the settings window. In the settings window, you find the actinic light list. To the left of these numbers, you find factor. This light factor allows the user to modify the range of actinic light intensities. The default value of the light factor is 1, and that gives actinic light intensities up to 1500 micromoles of photons per square meter and per second. If you lower the light factor to 0.4, you get a new range of actinic light intensities, this time up to 600 micromoles of photons per square meter and per second. If you change the light factor to 2, you get a range of values up to 3000 micromoles of photons per square meter and per second. By playing with the light factor, the user can get essentially any actinic light intensity he or she may want. The MINI-PAM-II has an internal light center. This has 2 consequences. In the report, the actually measured intensities of the internal actinic light source are indicated and not the values from the light list. And if the LEDs lose intensity due to aging, it is possible to click Calibrate after which the intensities are set in such a way that they are close again to the original factory values. Next, 3 functions you find in WinControl-3. First, the clock function. If you want to repeat a specific measurement, one indicated in the list on the slides, at regular intervals, it is possible to use the clock function. In such a case, the instrument will work for you, while you can do something else. One of the experiments you can choose is actinic light plus yield. This means that you apply a particular actinic light intensity for some time, and then probe the sample with a saturation pulse. It allows a relatively quick comparison between samples. It is a simple version of the induction curve and a short version of a light curve. The second button is F offset. If, in the absence of measuring light and actinic light, the fluorescence is not 0, there is an offset. And by adding this offset value in the indicated window and clicking Adjust, this value will subsequently be subtracted from all measured fluorescence values. Finally, the third function is signal LED active and beeper active. When the beeper box is checked, the instrument will give a beep each time a saturation pulse is applied. And when the signal LED box is checked, a double flash every 2 seconds indicates that the clock is active. The next window is the memory window. It is important for those of you that use the instrument standalone. In that case, the measurements made are stored in the memory of the instrument. To analyze those data, it is a good idea to transfer them to the computer. If the instrument is connected to a computer, then the WinControl software will list the data sets that can be found in the memory of the instrument in this window. I want to focus here on the Download Selected Files button. First, you have to select the files you want to download on the computer with the mouse. You can select more data sets using the mouse in combination with the Shift or Control buttons. If you then click on the Download Selected Files button, a pop-up window will show up. If there is still a file open and you do not want to merge, then you choose Clear Existing Data. I assume that you will almost always choose the Clear Existing Data option. If you then click OK, the data are turned into a report file. A logical follow-up tab is a report file tab. In the slide, the standard format of a report file is shown. In the standard format, only a limited number of parameters is shown: F, par, Y2, FM- and ETR. If this report is exported, only these parameters are exported. This is a report of a light curve, and in green I indicated Reg 1 and Reg 2. Reg 1, or Regression 1, gives the parameters of an eyeless and Peters-like fit, and Regression 2 gives the parameters of a Platetal-like fit. I want to point out that a decrease of ETR at high light intensities often has nothing to do with photoinhibition, but in most cases has to do with the very small fluorescence peaks on the basis of which the ETR is calculated. In many cases, the user may want to export more than just the basic set of parameters. In that case, more parameters can be selected as illustrated on the slide. If more parameters are selected, these are added to the report spreadsheet, and when the report is exported, these additionally selected parameters will be exported as well. From the report window, we go to the batch window. For those of you who want to do non-standard experiments, the batch window offers a quite practical application. It is called Record Macro. The first 3 steps are simple. Click New Batch File, then click the Edit button, and finally click Record Macro. Once you have done this, you are ready to record an experiment. So let's invent one. Let's assume I want to make my own induction recovery protocol. I have written it out, but not to get confused, it's a good idea to create a timeline which will tell you at what time point to click on which button. saturation pulses, actinic light on or off, etc. To translate my protocol, first, I do not want to end the light phase with a saturation pulse. Second, I want to make the transient F0' increase following lights off visible. So I do not use FR light on actinic light off. Finally, I want to go relatively quickly to a 1 minute pulse interval where I keep it. With a stopwatch next to me, I went through the sequence, and the not entirely perfect result is seen in the graph window. Once the experiment is finished, you have to go back to the batch window to uncheck record macro. This stops the conversion process. In the batch window, you see now the result of this process. The created batch file can be saved. When you want to run the experiment again, open the batch file in the batch file window and execute it by clicking Run. I can turn my protocol also directly into a batch file using the commands provided by the batch file window. The figure in the right bottom corner gives the first few lines of the manually created batch file. For field measurements, our leaf clips are quite practical. They have light and temperature sensors. On connecting the leaf clip to the instrument, a few things happen. Automatically, the parse star box is checked, and this means that the instrument switches to detection and recording of the ambient light intensity. In the software, the ambient light intensity and temperature are now monitored and shown. I want to show one potential side effect of the checking of the parse star box, which happened a few times to me. The slide shows a light curve with the parse star box checked. This means that the different light levels of the curve are assigned to the ambient light intensity and not the light intensity of the internal light source that was applied. The correct light curves can be restored by exporting the data to a spreadsheet program, where the user can replace the ambient light levels by the applied light intensities. In the near future, the software will be changed in such a way that it will automatically associate a light curve with the light levels of the internal light source. In our garden, we have a set of MICRO-PAM heads. They measure Laura serrace's leaves, and you can see these data on our website. This instrument measures temperature, ambient light intensity and humidity, in addition to fluorescence. It is possible to use a MINI-PAM-II with a 60-degree leaf clip as well for monitoring. However, there are a few differences. Low energy use is always important, but for our monitoring instruments, low energy use and remote communication are the top priorities. Some months ago, I downloaded data derived from this experiment from Walz.com. If you look on our website, the data could look a bit like this. With the different buttons, it is possible to make the time dependence of the different parameters visible. One of the things you can do with such data is to take the measurements from each day and turn them into light curves. Up to approximately 700 to 800 micromoles of photons per square meter per second. The points lay more or less on the same curve. At higher light intensities, the noise increases considerably. These light curves, I think, may help the analysis of such data sets. Monitoring measurements and field measurements are a completely different ballgame compared to light curves and induction curves that were discussed above. Based on ambient light measurements, it is always possible to determine Y2 and ETR. If the samples are monitored for several days, the F0 and Fm values measured during the night can be used as reference values for the calculation of photochemical and non-photochemical quenching. Field measurements give information about spatial distribution and heterogeneity of photosynthetic properties, whereas the monitoring of samples in time gives information on the response of the photosynthetic apparatus to environmental factors. One of the potential problems related to monitoring experiments is called pulse fatigue. If saturation pulses are applied with a relatively high frequency over a long period, the sample at a certain point may say, "I've had enough." Two things can be done to avoid this problem. The saturation pulse frequency during the night should be low, 1 pulse every few hours. And secondly, the saturation pulse frequency during the day should also not be higher than necessary, for example 1 pulse per 20 or 30 minutes. With a batch file, it is possible to program this. And with this, I finish this tutorial. Thank you for your attention.